Grab a small object nearby for a second. A pen, a coin, literally anything you can hold. Got it? Okay, hold it up and just let it drop. Now, as it falls, I want you to really focus and feel your own weight pressing down into your chair. That steady, downward heaviness, right? That is the oldest, most undeniable physical certainty that you and I know. It's pretty much the very first rule of physics we figure out as babies. But welcome to this explainer, where we are going to challenge exactly that feeling.
So what if that deeply human sensation is actually a massive cosmic illusion? What if gravity isn't a basic, ground-level ingredient of reality at all? For a century, we've just accepted gravity as this fundamental force pulling things together. But recent breakthroughs in physics suggest something totally different. Gravity might not be a fundamental pull. Instead, it might be an emergent behavior. Basically, something the universe just does while it's busy keeping track of hidden information. To understand how the floor beneath us might actually just be a surface stretched over something far, far deeper, we need to look at how modern physics got totally stuck in the first place. To understand why gravity is such a massive headache for physicists, we have to look at the family of fundamental forces. We've got 4 of them: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Now, over the 20th century, physics beautifully unified the first 3 into this single, elegant mathematical framework called quantum field theory. They all sit nicely together, right at the same mathematical table. But gravity? Gravity is the awkward outcast at the dinner party. It stubbornly refuses to join the others. And this is the quiet scandal of modern physics. On one side, you have quantum field theory for those other 3 forces. It makes predictions that are unbelievably accurate down to more than 10 decimal places. That's like measuring the distance between 2 major cities down to the width of a single human hair. It's wild. But on the other side, you have quantum gravity. Every single time generations of brilliant minds have tried to break gravity down into tiny quantum pieces, the math just completely collapses. It stops giving us useful numbers and just spits out infinite, uncontrollable nonsense. Let's trace how we finally arrived at a breakthrough. We started way back with Isaac Newton in 1687, who basically saw gravity as this invisible tether, a pull. Then Albert Einstein came along in 1915 and proved that gravity isn't a pull at all. It's actually the curvature of space-time itself. The heavy stuff bends the universe. But here's the catch. Einstein handed us a perfect rulebook, an equation that tells us exactly how space bends, but he completely left out the reason why it bends. To find that reason, we had to wait for the 1970s, the study of black holes, and something that initially seems completely unrelated. Okay, so to find that missing why, we have to talk about entropy. Now, you've probably heard entropy described as the tendency of things to get messy or disordered, like your bedroom, but that kind of misses the true beauty of it. Entropy is actually a strict mathematical census of hidden information. Think about a deck of cards. There's only one way it can be perfectly ordered by suit, right? But there's an astronomical number of ways you can shuffle it where it just looks like a random pile of cards to you. Entropy is literally just counting all those hidden, invisible ways the small pieces of a system can be arranged without changing how it looks on the outside. Which brings us to the 1970s, when physicists like Jacob Beckenstein realized something absolutely terrifying. What happens if you drop a hot cup of tea, which is totally full of entropy, into a black hole? Well, it vanishes past the event horizon. But if the tea's entropy just ceases to exist, it breaks the second law of thermodynamics. And that isn't just a suggestion. It's the ultimate taboo, the most sacred law in physics. You can't just delete information. To save the laws of the universe, Beckenstein, and later Stephen Hawking, realized the black hole itself must possess its own entropy and its own temperature to balance the cosmic books. But calculating this led to a truly bizarre paradigm-shifting discovery. Normally, if you want to store more information, say in a cardboard box or a computer hard drive, your capacity grows with the 3D volume. You double the space inside, you double the storage. Makes sense, right? But a black hole completely shatters this rule. Think about this for a second. Its capacity to store hidden information grows strictly with its 2D surface area, its event horizon. All the complex information it swallows is somehow just written on its flat outer boundary, not stuffed inside its volume. This meant black holes actually glow with a faint heat, what we now call Hawking radiation, and their gravitational boundaries obey the exact same laws as 19th century steam engines, which brought the physics world to a massive crossroads. Was this just a quirky coincidence happening in extreme, faraway cosmic objects? Or was it a massive, flashing neon sign suggesting that gravity and thermodynamics were secretly the exact same subject? And this points us directly to the concept of emergence,
Let's think about temperature for a second. A single solitary molecule doesn't have a temperature. Temperature is an emergent property. It's a large-scale summary of billions of invisible molecules bouncing around and hitting things. So if gravity has entropy and temperature, just like a black hole does, then gravity isn't a foundational pillar of the universe at all. Gravity is just a large-scale thermodynamic shadow cast by something much, much smaller.
Let's see how this plays out in completely empty space, far away from any black holes, with something called the Unruh effect. Imagine you are floating in a pure, perfectly cold, empty vacuum. Nothing around you. If you suddenly hit the gas and accelerate, something incredible happens. Your relentless motion actually creates a boundary, a horizon behind you from which light can no longer reach you. And simply because you are accelerating, that horizon radiates. You will actually feel a bath of gentle heat. The vacuum isn't absolute. Its warmth entirely depends on how you move through it.
So in 1995, a physicist named Ted Jacobson took these exact pieces and did something practically magical. He showed that if you stand at any point in empty space, look at that local horizon created by acceleration, and simply balance the heat and the entropy across it, the math forces spacetime to curve. Literally, Einstein's famous equation for gravity naturally falls right out of the thermodynamics of empty space. It's an incredible upside-down flip in physics. Thermodynamics is the deep principle, and gravity is just the consequence.
It was a beautiful derivation for sure, but it rested on one maddening mystery that haunted the physics community for 30 years. Remember, entropy is a count of hidden arrangements. It's a count of small pieces. So if Jacobson was counting the entropy of empty space to create gravity, the entropy of what exactly? What microscopic pieces of the universe were we actually counting in an empty vacuum? It's literally like having a final total on a grocery receipt, but absolutely no list of items to show for it. For years, we thought the answer was quantum entanglement, those spooky threads of quantum connections woven through the vacuum. But calculating that raw entanglement always resulted in meaningless infinite numbers. It was useless. Recently, however, a groundbreaking new paper finally solved this by using a clever tool called relative entropy. Instead of trying to measure the infinite total entanglement of the whole vacuum, relative entropy just measures the clean, finite difference when you add a tiny, almost invisible breath of energy to it. The infinite noise just cancels out, leaving a pure, totally usable number.
And this brings us to the staggering conclusion of this explainer. When you use this finite measure of relative entropy, that gaping hole from 1995 is finally closed. Space-time bends simply because the entanglement entropy of the quantum fields absolutely demands it, just to balance the universe's ledger. Let that sink in. Gravity isn't some invisible force pulling things together. It is quite literally just the thermodynamics of quantum entanglement. And honestly, this brilliantly illustrates why we spent 100 years failing to find a quantum particle for gravity, the mythical graviton. Think about sound. Sound travels in waves through atoms, and we can mathematically treat sound as little packets called phonons. But phonons aren't real fundamental particles. They're just the collective ripple of a whole crowd of atoms. Trying to quantize gravity is exactly like trying to find a quantum particle of sound inside a single silent atom. You can't do it. Gravity isn't the atom, it's the ripple. This completely changes how we should view our daily experience. When you watch an apple fall from a tree, you aren't seeing an invisible rope pulling it down to the earth. You are watching cosmic bookkeeping made visible. The massive presence of the earth tilts the accounting of the quantum fields, and the apple just naturally drifts along the absolute cheapest thermodynamic line the universe offers to balance its entropy ledger. It's falling because it's the most efficient thing to do. Now, bring this right back to your own physical body. Remember that heavy pressure you felt in your chair at the start of this explainer? That undeniable, grounded sensation you've trusted since you were a child. It is just your body being stopped by the floor from taking that cheapest thermodynamic path. You are literally leaning against the cosmic ledger. Your weight is just information made heavy. You are existing inside a massive, invisible calculation happening at every single point in space. But in physics, every answered question is really just a door to a bigger room. We finally know gravity emerges from the entropy of quantum fields. But if entropy always counts the arrangements of something smaller, what on earth are the quantum fields made of? We finally found the floor, only to discover another trapdoor right beneath our feet, leaving us to wonder what deeper, nameless layer of reality lies just beneath our everyday, very human illusion of weight.